In this problem, we are going to find the magnetic force between two current-carrying wires. One wire is a long straight wire. We are going to assume that it is infinite because for an infinite wire, we have already computed the magnetic field produced. The other wire is rectangular in shape. All right. So let's remember that when we are computing the magnetic force, the magnetic field is a mediating field. So that means I need to compute the field produced by one of the currents, and then I'm going to find the force applied by that field on the other current. So obviously the natural choice is to use, first start with this infinite wire, compute the magnetic field produced by that wire, and then compute the force applied by that field on the second, on the rectangle. But you can do it in the other way around. How do I do this? I have a rectangle in here. Well, all the sides are straight. We haven't computed the magnetic field produced by a rectangular frame, but we can. That's also a possibility. But we have to construct the integrals again, but the integrals will have now limited bounds, but they can be evaluated. So as a result, we can compute the magnetic field produced by that rectangular frame at points on the on that straight line in here. It's going to be a complicated expression, which will also depend on position, but we can. And then, of course, I can compute the magnetic force applied on the straight wire. But of course, this will also involve some kind of an integral. In any case, by using this, we can compute the force applied on the straight wire. But at the end, I know that whatever that force is, let's just draw an attractive force in here. Whatever the force on the straight wire is, I know that an equal and opposite amount of force should be applied on the rectangular frame because of Newton's third law. So as a result, I can compute the magnitude of the force in one of these two equivalent ways. And since we would like to solve problems in the simplest possible way, we are going to do it in the first way that I have described, right? Basically, I'm going to compute the force applied on the rectangular frame. For this, I'm just going to use the magnetic field produced by that infinite wire. And that's the one that I'm going to describe in here. So let's just start with the magnetic field. All right. So the arrows are drawn like that, and the currents are labeled as I1 and I2, but the problem doesn't tell us whether this I1 and I2 are positive or negative. Presumably, when we find the final solution, that final solution would be valid for all of the possible values of I1 and I2, including positive and negative values. But I'm going to draw diagrams, draw arrows for vectors, assuming that both I1 and I2 are positive. But at the end, we can perhaps investigate the final expressions and see that if the currents are negative, then these expressions also make sense. But I'm going to do the discussion at the very end. All right, so therefore, let's start with this infinite wire in here. Right, there's a current flowing to the right. So this is the direction of the current. And so therefore, by the right-hand rule, at any points in the upper half plane in here, the magnetic field should be pointing out of the board, out of the screen towards us. And in the lower half plane, the magnetic field should be pointing into the screen. Just remember that the magnetic field is just this three-dimensional thing. They actually form these circular magnetic field lines in these 3 dimensions. But I'm looking at the magnetic field in this plane of that figure. So this figure fits on a plane. So since the magnetic field is perpendicular to that plane, I just denote the field by these symbols. So this dot symbol expresses the fact that the magnetic field is pointing towards us. But this cross symbol just expresses that this magnetic field is pointing away from us, right? Both of these vectors. Let's remember that these vectors have these magnitudes, mu 0 I divided by 2 pi r, where r is the distance from the wire. Let's just keep this in mind. All right. So another thing is, of course, the magnetic field is not uniform. So it has different values at different points on the circuit. So as a result, at these points, the field has different values. But at least I can say that all points with the same distance from the straight wire should have the same magnetic field. So as a result, I can say that the magnetic field at all points on this edge in here, on this edge, which is closest to the infinite wire, has the magnetic field given by, I'm going to call this as B1, mu 0 I divided by 2 pi r. On the far edge in here, again, all the magnetic fields have the same value, have magnitude and value too. So that's mu 0 I divided by 2 pi r plus a. On the other hand, on this edge and the other edge, the magnetic field is not uniform. So it is basically larger at points which is closer to the infinite wire, and it becomes weaker as we move move away from the straight wire. So as a result, the magnetic field is not uniform there. To find the force, of course, we need to evaluate an integral. So that's going to be the difficult part of that problem. But probably we can even solve the problem without evaluating this integral. Let's see what happens. So in this diagram, I'm going to show the directions of the forces. Let's show the directions. Again, I'm assuming that I1 and I2 are positive. So let me show the. I'm going to use. Let me use this color to show the direction. So first, let's remember that the force is equal to the current length across the magnetic field. So then in that case, of course, it's the current in the second circuit, but the magnetic field produced by the first. Right? Let's just remember that. And L is the length vector on the second circuit as well. So as a result, on this edge in here, which is closest to the straight wire, length vector is pointing towards right. Magnetic field vector is pointing towards us. This is magnetic field. So L cross B is a vector which is pointing downward. Right? So as a result, this vector is now downward. So I'm going to call this force as F1. Right? So that's the correct direction. So let me erase the unnecessary confusing details now. So I use the right-hand rule by using this three-finger rule that relates the vectors in a cross product. So this force is F1. What is the force acting on the other edge? On this edge, right? Let's just let me draw the vectors with the same color again. So this time the length vector is towards left. How do I choose the length vector? Because it's the vector that is parallel to that direction that I have used for expressing the current, right? So it has a definite direction. So the current and this length vector must be consistent with each other. So length vector is towards left. Magnetic field is still upward. So L cross B, I'm using the right-hand rule with my three fingers. My middle finger shows the direction away from the side. So therefore, I draw the force vector like that. So I'm going to call this F2. Let me erase again the details in here. All right. So as a result, we know the directions of these two forces. The point of application of the forces. Of course, since in this case, the force applied on each part of that wire has the magnitude proportional to the length, you can kind of guess that the total force can be assumed to the geometrical center of that wire. So that's basically the midpoint in here. So both of them should be acting at the midpoint. So when you want to compute the torque, of course, you may need to find that point of application. But in any case, we have a situation like that in here. So you can see that, of course, the magnetic field somehow tries to extend the area in a way of that rectangle. So, and the reason is, of course, that this thing appears is that the magnetic field has the same direction everywhere on that rectangle. So as a result, by using this, you can also guess the direction of the force in the other two sides. So therefore, F3 will be like that, and F4 will be like that. All right, let me also erase this A in here. So as a result, we can just clearly see all the forces. Now about the magnitudes, I can say that this F1 is bigger than F2. So as a result, if I'm computing the net force will be attractive then. And the second thing is that F3 should be exactly equal to F4, because essentially the magnetic field values, the magnetic field is a variable, but this magnetic field somehow has the same dependence at these two sides. So therefore, if I evaluate the integral, I'm going to evaluate the same integral. So as a result, the magnitudes would be the same. So as a result, these two forces are the same. So let me just write this thing down like that. This F3 is equal to F4. Again, let me state this. This is a notation that I use a lot. Whenever I draw an arrow and a scalar number, a scalar symbol next to an arrow, I mean that, by this symbol, I mean that this scalar in here is the component of the force along that direction. So this is basically, there's a force in here, it's a vector. So that's the component of F2. There's an F2 vector in here. There's a vector. And this F2 scalar is the component of F2 along this direction. Which direction? The arrow, the direction shown by the arrow. So as a result, for example, in here, there is no problem in writing F3 is equal to F4, because F3 is the component of the force acting on that side along the rightward direction, which means that the corresponding vector is towards right. And F4 is the component of the other force along the leftward direction. And so again, as a result, these two forces, F3 and F4, as vectors, they are opposite in direction, so they are not equal. But the component of this force, F3 force along rightward direction, is equal to the component of this leftward force in the leftward direction. So as a result, this makes sense mathematically, but of course the F3 vector is exactly opposite to the F4 vector, right? So again, the vectors are different, so there's a relationship between the vectors like that. So this is a correct relationship. The same relationship would be valid if I'm expressing this in terms of the components along the same direction. For example, the x component of F3 would be equal to the x component of F4 with a minus sign in front. But in this relationship, I'm not expressing the components of these vectors along the same direction. These are components of vectors along different directions. So F3 is expressed with this direction and F4 is expressed with that direction. So as a result, along these directions, this makes sense. Of course, this is intuitively what you do, right? When I write down this kind of an expression in here, with F3 being equal to F4, I say, this makes sense, but of course you have to just keep in mind that particular detail in here. So in any case, less than, let's forget about all the details in here. Let's just go ahead and compute all the forces. So let me erase everything in here. Erase this one too, and the force is in there. So in any case, so I can say that F1 is, I'm just going to write down the magnitude in here, is the current multiplied with length multiplied with B1. Just remember this. But the current is I2. Length is B. And the magnetic field is mu 0 I divided by 2 pi r. Mu 0 I1 divided by 2 pi r. Right, this is also what I have called as B1 in the previous picture. So as a result, this is like mu 0 times I1 times I2 divided by 2 pi B divided by R. Right, let's just write it down like that. F2 would be the same. That's going to be, let me also write this thing down. This is I2L B2, but this time by B2 I'm applying the magnetic field created by that straight wire at the locations of this far edge, right? This is that's the subscript that I have used in the previous picture. In here, I have called the magnetic field in here as B2 and the magnetic field in here as B1. Just remember this. All right, so as a result, I mean, the calculation is going to be the same. So therefore, let's just say that this F2 is then mu 0 I1 I2 divided by 2 pi, length is B, and the distance is R plus A. So as we have expected, this is smaller in magnitude. And then finally F3, which is equal to F4, I don't want to compute these. So as a result, I write who cares. If you want, I can also, it's not a question mark, I'm sorry. Who cares? It's not a question. It's just an expression that tells us that I don't care. But if you want, I can compute these as an integral expression. So this can also be computed. It's a very simple integral, actually. But to solve the problem, we don't need this. In any case, so as a result, I'm going to draw this picture in here. So we have this rectangular frame. So therefore, the net force is along this direction, and it has a magnitude given by F1 minus F2. So we can compute this. F net therefore has a magnitude mu 0. I'm saying magnitude in here, but that's also a component of that force along this direction, but I'll talk about this in a moment. So that's 2 pi. There is B in here divided by R, and B divided by R plus A. So if I then subtract these, I'm going to get mu 0 I1 I2 AB divided by 2 pi. AB is divided by R plus A. All right. So that's the answer to our problems. Right, that's the force applied on. Let me use this color again for the force. So this is the net force. What's the point of application? That's not that important. So as a result, let me extend this a little bit so it's not just the force applied on a side, right? It's the force applied on the whole system, actually. So on different sides, of course, there are different forces applied. So this F net is the sum of all of these forces. So then let's talk about this, the signs. So I have derived everything assuming that I1 and I2 are positive currents. If they are indeed positive, then this arrow shows the correct direction of the force vector, the net force on the rectangular frame. But if that's not the case, so for example, just think about the situation where I1 is negative and I2 is positive, right? But still the same directions are shown in here, right? Which means that on the straight wire, the current in the leftward direction is minus I1, which is positive, right? The positive current flows in the leftward direction on the straight line, which means the magnetic field in the upper part of this plane is into the screen. All right, let me also erase this. So what happens then? What happens for this situation? This formula is still valid, but this time you're going to interpret this expression in here not as a magnitude, but as a component of some vector, which is the force vector, net force vector, along this arrow, right? So just take this as for example, your y-axis. So therefore, this number is the y component of your force. So you can see that this formula in here should be still valid, because in that case, F net formula gives us a negative value, which means that there's a force in here whose y component is negative, which means whose component along this minus y direction is positive. So that's the component in that case along that direction is minus F net, which is positive along that direction, right? In that case, therefore, the force is repulsive, right? Let's just remember this. So let me erase this again, extra pictures, extra symbols. So we have this relationship in here. So this is F net, right? Let's also erase everything in here. So what we have said in here, therefore, I mean, if I1 and I2 are both positive, then this is an attractive force. But if I change the direction of the current I1 and don't touch to I2, in that case, the force also changes direction. So that's reasonable, right? Because when the current is zero, of course, the force is zero. As a result, when the current changes sign, the force also should change sign. That's perfectly reasonable. What happens if both of them change signs? So both currents somehow reverse. In that case, the force will still be in the same direction, right? So in any case, you can play with these ideas. Another thing that I'm going to do is this. In some other video, I have solved a problem about the magnetic force between an infinite wire and a dipole, and an atomic dipole, for example. We have just computed this thing, but by using a different mathematical procedure. In that case, we have just computed the magnetic potential energy of the magnetic dipole in here by taking this dot product minus mu dot B, and then we took its derivative. So it is interesting to see if we can obtain the same answer to the previous problem by using this problem, because in this problem, let me erase everything in here. This is actually for a rectangular loop, but the rectangular loop can be considered as a dipole. It's not a point dipole. It has a size, but by taking a limit, of course, I can make sure that the size is negligible. So let's do that then. So what happens is that first I need the magnetic dipole moment magnitude, right? So that's I'm going to call this as mu2, right? So this is current multiplied with the area. This is just the magnitude. I also need the direction. So the direction in here is, we use the right-hand rule. Basically, let me show the right-hand like that. This is again a three-dimensional picture, but probably you're going to understand. Your four fingers show the direction of the current. In that case, your thumb shows the direction of the area, and in that case, of course, the area multiplied with the current gives you the magnetic dipole moment. So by using the right-hand rule, you can see that the magnetic dipole moment in that case is pointing towards us. Right? So we have this situation in here, and the magnitude of the magnetic dipole moment is I2 times AB. So let me erase this 2 as well. So what I need to do in that expression is to erase this I2 in here, erase this A times B, which is the rectangular area, and write mu2 in there. Right? That's the first step. The second step is the small size assumption, small dipole assumption. So in this assumption, we are assuming that the size of the dipole is much smaller than all the other length scales that appear in your problem. So in our problem, the only length scale that appears is the distance to the rectangle. So as a result, we are going to assume that the size of the rectangle is much smaller than that distance. Right? In this case, this actually implies that I can neglect this r plus a in this expression in here, because that's the only place where the length a appears, and so therefore we are just going to neglect it. So that means I'm going to replace it with 0, which means I'm going to do the change on the equation in here. Perhaps it's not a good style, but I'm going to do it. So that's therefore mu0 I1 multiplied with mu2 divided by 2 pi r squared. Right? Did we find the same result before? Probably yes, we did. But let me draw this picture again. So we have a wire that carries a current I1. I have a dipole in here mu2. I know that this I1 produces a magnetic field in here. Let me call this as B1. This pointing out of the board, out of the screen. So the magnetic potential energy is equal to minus mu2 dot B1. So since they are in the same direction there, that product is equal to the product of their magnitude. So therefore this is mu0 I1 divided by 2 pi r mu2. That's the magnetic potential energy. And then we said that, let me show this radially outward direction like that. So this is the direction where this radial distance increases. So the component of the force in the radial direction is equal to the negative of the derivative of the potential energy. So we have a minus sign from here, another minus sign coming from there. A third minus sign comes from the derivative, and then the other things in here. So we have 3 minus signs, so that's going to produce mu0 I1 divided by 2 pi r squared times mu2. This is the component of the force in the radially outward direction. So therefore, in the radially inward direction, therefore the component would be positive. So this is the component in the radially outward direction. So that's how I would write down this expression. But in the radially inward direction, the component would be positive, right? So as a result, you see that you get the same direction and same magnitude. Okay, so as a final step, I said that I'm going to compute the magnetic force acting on the size of that rectangle as an integral. Let's just do this. But I mean, this is just a technical detail, so if you are interested in this detail, just follow the rest. right? So r is the distance in here. R plus a is the final distance. I'm considering the magnetic force acting on this right side. Right? In that case, the magnetic field is pointing out of the board, out of the screen, and the current is flowing along that direction. Right. So what we do is this, I need to invent a new variable. So since I have used r as a constant in here, I don't want to use this the same letter for some other symbol. So I'm going to show the position of a point on here by the letter r prime. Right. This is also a radial direction, but I mean, this is the symbol that I'm going to use. Because I need to find a name that's different than the constant that I already use. So next thing is, of course, let me magnify this place in here, all right? So I'm magnifying this because I need some space in here, right? So as a result, the wire is in there. So r prime is that distance. So what I do is I just consider a small piece in here with a length dl. So this dl has a magnitude of dr prime. So as a result, I'm essentially computing, considering the portion of the wire with a radial distance between r prime and r prime plus dr prime. All right. So this is going to be my length vector, but I'm not going to write this thing down in unit vector notation because I know the directions. So that part is not going to bother me at all. But I just need to compute the force. So for that purpose, let me erase this side of the picture. So the force that acts on that side, I'm going to write this thing down as a differential, is equal to, let me first write down the vector expression. It is equal to dl cross the magnetic field. Again, the magnetic field is due to the infinite wire. But we know the direction, so dl is upward, magnetic field is out of the screen, so therefore df is to the right. So let's just show it like that. That df3 is a vector pointing towards right. Let me not put the sign in here. So in any case, in that case, the component of df3 in the rightward direction is therefore equal to I2 times the length in here, which is dr prime, multiplied with the magnetic field. So therefore this is I2 times dr prime. Magnetic field is mu0 I1 divided by 2 pi r prime. R prime is the variable in here. So let's write it again. So again, this is in the simplified form, dr prime over r prime. So as a result, we have an expression which is a constant multiplied with an expression that involves the integration variables. We only have to make sure that all variables are expressed in terms of the integration variables in here. That's the only step. So finally, f3 is the integral of this df3. So that's equal to, I'm writing the constant portion out of the integral. And we have the integral of dr prime over r prime. What are the integration limits? R prime starts with r and ends up with r plus a. So let's just go back and see it in here. Where was it? Yeah, it was in these pictures. But in any case, we start from here where the distance is r and end up in here where the distance is r plus a. Right? That's what we are doing. All right. So therefore, this is the integration. These are the integration limits. So the integral is logarithm of r prime r. Right? So therefore, I can write down the integral as logarithm of r plus a minus the logarithm of r. I can also express this in terms of the ratio. All right, that's how you compute that force, but let me just write in one final place. So F3 therefore is equal to mu 0 I1 I2 divided by 2 pi and the logarithm of r plus a divided by a. Let me go back and check if everything is correct. Yes. So you can also check the essential features in here. The force should involve both currents and it should involve both currents linearly. Force should be proportional to both of them. Because if one of the currents is zero, then the force has to be zero. You can also check the dimensions, but usually these kind of things they are not easy to check with the dimensions. But if you are used to this, then you can also check the dimensions. So let's remember that mu 0 has the units of newtons per ampere squared, which means that if I multiply mu 0 with two currents, then I get an expression with the dimensions of force. And we have a similar situation in here. So mu 0 multiplied with the two currents, and the rest is a dimensionless expression. As usual, the argument of the logarithm is a dimensionless number. It's the ratio between two lengths.